Right, today we're talking about section 1.3, evaluating limits analytically. So, what have we discovered about limits? Is it necessary to do a chart and graph every time? We hope not, because that would be an awful lot of work. So there's two categories, one where direct substitution works and one where direct substitution doesn't work. When it worked, we had simple functions like this. Very simple. As x gets close to 4, and we can test it on our calculator, and you can figure out what the limit or the y value is as x gets close to 4. Here, as x goes to 0, you would have, if you substituted a 0, you would get a 0 over 0, which I like to call, oh no. Okay, and we can't have that. So that means we are in indeterminate form, and we have to do something with that. Also, when we have number over 0, we have to look at that. There's special things that happen there too. So let's look at some very easy examples. The limit as x goes to -2 on 3x minus 4. We simply can substitute -2 in, and we get -10. What about the limit as x goes to 1 on negative x squared plus 6? 1 squared is 1, negative times 1 is -1, plus 6 is 5. Simple enough. When we go to -1, we can substitute -1 here. Again, watch your signs, your algebra is going to get you. And we get -9, because this is a -1 squared, which is positive times the -2. If I take the limit as x goes to pi on tangent, well, the tangent of pi is 0, so that's 0. And if I look at this one as x goes to pi on cosine of 3 times pi is -1 for cosine. So let's remember, you need to know your unit circle values. Theorems which support these ideas, there's quite a few here. They're real simple. The limit as x goes to a, some value for x, on a constant function is the constant function. Here's an example. The limit as x goes to 3 on 7 is 7. Think about the line y equals 7. It does not matter what x is, y is always 7. All right, the identity. The limit as x goes to a on the function x. Well, that answer is a. Think about it. The line y equals x, whatever x equals, y equals. So that's pretty easy. The limit of a power. Let's look at the limit as x goes to a of x to the n is the a to that nth power. Think about it. As x goes to 5 of x cubed, that would be 5 cubed, which is 125. Or I could also think about this as the limit as x goes to 5 on x, which would be 5, and then cube it. You know what the cubic function looks like, so again, not too terrible. Those were some basic rules. Here are rules you must know. The limit as x goes to a of c times f of x. C is a constant. So the constant can be brought out in front of my limit notation. I can find the limit as x goes to a on my function and multiply by it the constant. So the limit of a constant times a function is the constant times the limit of the function. Look at the example. The limit as x goes to 3 of 2x. This 2 is a constant multiple. I can bring it out. And now I have 2 times the limit as x goes to 3 on x. This is the identity function. As x goes to 3 on x, this value is 3, that limit, times 2 is 6. All right, here it looks like we're taking the limit as x goes to a of f plus g or f minus g. And it looks like we're just going to say the limit as x goes to a on f plus the limit as x goes to a on g. That is our sum or difference limit. The limit of a sum is the sum of the limits, or the limit of a difference is the difference of the limits. And here's an example that illustrates that. Likewise, the limit of a quotient is the quotient of the limits, as long as the limit on the bottom is not 0. And the limit as x goes to a of some function to the nth power is the limit as x goes to a on the function, then raised to the nth power. Same thing happens with fractional exponents. The limit of a power is the power of the limit. Okay? You need to know these well. Limits of polynomial and rational functions. If p is a polynomial function, and a is real, then the limit as x goes to a on my polynomial function is p of a. In other words, we can just direct substitute in. If r is a rational function such that r of x is p of x over g of x, so one polynomial over another, and a is real, and q of a is not 0, then the limit as x goes to a is r of a, which is p of a over q of a. Now, I'm going to say you need to check for a 0 over 0 or a number over 0. This is going to mean more work, and we'll look at that when we look at some problems in class. The limit of a function involving a radical. Obviously, the limit as x goes to a of the nth root of x is the nth root of a. Now, let's remember, if I'm taking an odd root, then this is valid for all a's, whether a is a positive or negative number. But if we are taking an even root, second root, fourth root, sixth root, remember that your a cannot be negative. Now, this one can be very complicated, and there's a lot of little nuances on this one. So we're going to investigate this one throughout the semester with interesting type problems. It's the limit of a composite function. When you take function f and g, and they are functions such that the limit as x goes to a on g is L, and the limit as x goes to a on f of x is f of L, then we can say the limit as x goes to a on f of g of x is f of the limit as x goes to a on g of x, which is f of L. Now, a lot of times that's true. What we're going to do is apply the limit to the interior function. Now, sometimes the limit, when you apply it to the interior function, does some interesting things, and we really have to look closely at what is going on. So this is a rule that can have some very interesting outcomes. We'll look at more of that later. We will look at the handout from Anton's Calculus in class. Let's remember that with our trigonometric functions, we can just simply substitute our value we're getting close to. And now we have 3 rules. When we find limits as x approaches some number, we're going to substitute. If I get a real number, that is your answer. If you get 0 over 0, or I like to call it oh no, we're going to do something algebraically, and then we're going to substitute. We'll talk about that in a little bit. So oh no means do more work. Evaluating limits when substitution does not work. Substitution doesn't work when we get indeterminate form or a 0 over 0. And if we get that, we have to do something algebraic, and then we substitute. So let us look at an example. If we look at this, you can see that if we substitute as x goes to 2, a 2 in here, I have 6 minus 6, so that's 0 on top, so I'm already worried. And then I have 2 minus 2, that's 0 on bottom. That is a 0 over 0, that's an oh no. In fact, we don't really ever write that. That is mathematically bad. But what can we do here? Do you see that we could factor a 3 out of that? And if we factor a 3 out of the numerator, we get this. And look, the x minus 2 can cancel. I am now looking at the limit as x goes to 2 on 3. That's a constant function. That means y value is 3 no matter what x is. And so my answer is 3. So this is the same as y equals 3 with a whole at 2 because we have a removable discontinuity. That's a word we're going to learn. We canceled out the factor where when x is 2, this factor gives us 0. So now let's look at this. If I substitute 3 in here, I get 9 minus 9 over 3 minus 3. So I have an oh no. That means there is more algebra that can be done. And so the algebra that we can do is factor that difference of 2 squares and cancel the factor. I'm canceling a factor. I'm removing it. What would make this factor 0 would be when x is 3. So I'm going to have a whole when x is 3. I'm going to have my limit as x goes to 3 of x plus 3, substitute our 3 in, and we get 6. So the graph is the same as the line y equals x plus 3 with a whole at x equals 3. Now, very important, I want you to see that you have to carry your notation until you substitute for x. Do not drop that limit notation. Also, when we look at the limit as x goes to 3 of the quantity x plus 3, we want to put that quantity in parentheses. This is bad form. Parentheses matter. So when we look at this problem, it looks horrible. But again, it's just algebra. But we can see that if we substitute 0 in, we're going to have a problem right there. And we're going to have a problem right there because on top, the limit as x goes to 0 on top is going to give us 0. The limit as x goes to 0 on bottom is going to give us 0. So we have to do something kind of strange. We are going to create a difference of two squares. We are going to multiply by the conjugate of what is in the numerator. That means we're going to multiply by the square root of x plus 1 plus 1. And we're going to show that step. So the limit as x goes to 0 of our original function, and we're going to multiply by the conjugate. Now let me remind you, even though it looks really ugly, this is really a minus b times a plus b, and a minus b times a plus b is a squared minus b squared. So when we square this, we get the quantity x plus 1. When we square the 1, we get minus 1. And we're going to leave the denominator in factored form because we might have something that cancels. Well, when we do the algebra on top, x plus 1 minus 1, I'm left with x. And notice this x cancels with that x because we left the denominator in factored form. And that is going to leave this. Now, here's what's nice about this. 1 over the square root of x plus 1 plus 1. That is never going to be a 0 over 0 because on top we have a 1. When we substitute 0 for x, we get 1/2. What this means is, as x goes to 0, this function gets close to 1/2. However, x will never actually equal 0 because we removed that possibility when we made this cancellation. But what it does say is, on this function, as x gets very close to 0, the y value gets very close to 1/2, and we have a hole at the point 0 and 1/2, because that is where x is 0. Now, the remainder of this page we will talk about in class. Your TPs from section 1.3, the try it problems, 9, 15, 24, 33, 37. See you in class.